cases. For linear polarization, this is what you have, and where these are the dynamical parameters. Alpha is the angle between the outgoing momentum and the direction of linear polarization. This C is the total cross-section here. And if you look at the asymmetry, where this term cancels out, because cosine squared of the angle alpha is always positive. Whereas this term, if alpha is 0, you get a positive number. If alpha is pi, this becomes -1. So if you take this for alpha equals 0, subtract the result for alpha equals pi, you focus only on this interference term. And that gives you this, where these are three different dynamical parameters, which I can show you what they are in a second. The carrier envelope phase is analytically extracted here. There's no carrier envelope phase dependence to these dynamical parameters. And we can simply write this as some dynamical factor, rho, which is the sum of these three parameters, and a phase, because these are in general complex. And so this says that the difference for linear polarization is some number times cosine of the carrier envelope phase plus another dynamical parameter. So there are two dynamical parameters if you fit this equation to an experiment that measures this difference. These are what the gammas actually look like, and we actually calculated these for atomic hydrogen, starting with the 1s state. This is a two-photon transition where you can produce S to S or S to D waves, and these are the matrix elements. These can all be done analytically for hydrogen. And let me show you. For circular polarization, in a similar way, you get a differential probability that depends on cosine of the degree of circular polarization times the angle in the polarization plane minus the carrier envelope phase plus a dynamical angle, which is the argument of these two dynamical parameters. And for elliptical polarization, you can write the differential probability in terms of two new dynamical parameters, a circular dichroism parameter that depends on the degree of circular polarization only and is maximal for circular polarization. But there's also a new elliptical dichroism term that is 0 for either circular polarization when L is 0, or for linear polarization when xi is 0. So it only exists if you have elliptically polarized light. And these parameters, these dynamical parameters, are invariant to a change in the polarization. So let's look for hydrogen, where we can calculate everything analytically as well as solve the time-dependent Schrodinger equation. This is our pulse. We choose a cosine squared temporal envelope for the A vector, and the electric field is the time derivative of the A vector. These were published in this paper, and these are the results along the positive z-axis and along the negative z-axis. These are our perturbation theory with analytical evaluation of the hydrogenic dynamical terms, and this is the time-dependent Schrodinger equation result. And you see the perturbation theory works extremely well. This is just a higher intensity. But now if we subtract those two terms, so we take here the results along the positive z-axis and the negative z-axis and subtract them, you see this asymmetry. And you see that the asymmetry crosses. And the asymmetry exists when the vector potential has this shape. And you can see why this is true, because here you have, this is much higher than at these ends. Whereas here you have a very symmetric behavior, positive and negative. And so here the asymmetries are for this carrier envelope phase are rather small, whereas for this carrier envelope phase they're quite large. And there are two different physical effects here. Here, this is the interference of the one photon amplitude with the two photon amplitude involving absorption and emission of light. That's what causes this difference. Then you cross over to the regime where you have interference between one photon absorption and two photon absorption. And that interference is causing that difference. And the difference switches sign at this point. And this just shows you using theoretically different Gaussian shapes and cosine squared shapes. You see the same qualitative features. And so for a theorist, either one will show qualitatively what would be measured in the experiment. And if you ask an experimentalist, it's difficult to know how to parameterize their pulses. This is, if you have a general elliptical polarization, the differential probability times the direction of the ionized electron integrated over all angles in the polarization plane gives you what is called the weighted momentum direction, or WMD, which does not mean weapons of mass destruction. For linear polarization, you have this result that I showed you already. Lars Madsen, for circular polarization, pointed out that the peak is not at the carrier envelope phase, but is shifted. And as we show in our paper, this shift is due to the complex phase of these dynamical parameters. And let's see, let me, in the interest of time, go on here. Let me show you, in general, this very neat result that we discovered with this, these weighted momentum distributions for 3 different polarizations. This is the magnitude of the weighted momentum, and this is the phase. And this is the ellipticity. This is in the polarization plane, this is the ionized electron angular distributions. So start out with linear polarization here, the black line. You have this asymmetric distribution, and the weighted momentum direction is along the x-axis, this axis. That gives you the maximum value of this weighted momentum distribution. The degree of circular polarization is 0 for linearly polarized light. Now let's look at circularly polarized light. You have right and left circularly polarized light. There are these two curves. There are these two curves here. You can see that they shift. The darker one is at the top here, whereas the darker one is of lesser intensity in this direction. And the weighted momentum direction for right circularly polarized light is here, and it's for left circularly polarized light, it's here. For an elliptically polarized light, right and left, you get these weighted momentum distributions. The blue colored curves show you the difference. And you have this neat result that as a function of ellipticity, the magnitude of the weighted momentum distribution has this nice shape with the maximum and linear polarization, but the phase angle is monotonic. And so if you have a pulse that you don't know its polarization, if you measure this weighted momentum distribution, the phase that you obtain will tell you the ellipticity of your pulse because of this monotonic relationship between ellipticity and the angular distribution. So to conclude this thing, this first part, short laser pulse ionization can be parameterized. We had other papers dealing with chirp, but I'm not going to discuss that. The carrier phase, the polarization, also the chirp, but I haven't discussed that. And the angular dependence of ionization have been analyzed for an unpolarized atomic target. There are new circular and elliptical dipolarism effects predicted, and perturbative results are in excellent agreement with time-dependent Schrodinger equation results that were done for the H atom analytically and numerically with the TDSE. So now I want to show you an example of what role electron correlation played, because all the results before were in the single active electron approximation or for hydrogen. Let's look now at how electron correlation affects things. This was published in 2012 in this paper. And these are the parameters of the pulse we're looking at. We did our calculations in two different ways and worked out the bugs in each of the ways so that the two different calculations gave the same result. I note that whenever you ionize a system, how do you produce a probability for ionization? Well, numerically, you have to propagate in time, and then when the pulse is over, you project onto eigenstates of your target system at that point. And we can project onto correlated target systems in the absence of the field or uncorrelated. And it's interesting to view the difference in these two projections, because that tells what the role of correlation is. So this is the differential probability. These are the different partial waves that you propagate in time, and then you can project onto some core function. And the absolute asymmetries that I will show you are the difference between an angle for linearly polarized light along the positive z-axis and the negative z-axis. This difference is the absolute asymmetry. You can also calculate the energy integrated absolute asymmetry, which is just integrate over all possible energies in your calculation with reasonable limits. And this difference at each energy, and that gives you a number that depends only on the carrier envelope phase, where the notation in these slides is different from the previous ones. So this is helium with 230 attosecond pulses, 2 petawatts, which is much more intense than any attosecond pulse that have been produced so far. At least 3 orders of magnitude more intense. Let's look at these curves, and I'll guide you through it slowly. Theta equals 0 curve is the top one. So this is measuring all electrons that come out in the hemisphere along the positive z-axis. Theta equals pi is measuring all electrons that come out in the hemisphere surrounding the negative z-axis. If we had monochromatic pulses, this is where absorbing 1 photon would put the electrons, we would put them here. If you absorb 2 photons, it would put them here. Because of the broad bandwidth, we get a spectrum that spans this space. And our projection onto uncorrelated functions is in excellent agreement with our projection onto correlated functions everywhere except in this region, between about 33 and 55 eV. These curves project onto uncorrelated or correlated agree almost exactly everywhere except here. And what's happening here? Well, these are doubly excited states clustered on the n equals 2 state of helium. I can blow up that region. So this is a fine energy scale between 35 and 36 eV. So here is 35 and 36. So right in this energy region, right around there, is where we're focused now. And you see remarkably that you have peaks that you can identify as the 2s, 2p singlet p odd doubly excited state of helium and the 2p squared singlet d even state of helium. Notice that these are even parity and odd parity. So this is prima facie evidence that you have interference of one photon and two photon amplitudes. If you change the carrier envelope phase from 0 to pi over 2, you see that these curves shift. So there's the peak drops. This is all along the positive z-axis. If you look at the negative z-axis, you get the same two peaks at the same energies, but their magnitudes are very different. So there's a huge asymmetry if we subtract this from this. And you can see that these curves, they differ by the carrier envelope phase. In this region, by the way, the projection on the uncorrelated states produces these lines, flat, because the uncorrelated states don't see these doubly excited states, whereas our correlated wave functions do. If I take the difference in those previous two slides, this shows you that this difference is, this is between 35 and 36 eV. So it's the difference of those two previous slides. These are the two peaks, and these are the results for two different carrier envelope phases. And you can see that the asymmetry is huge. So we like to say it's enhanced by electron correlations, as opposed to this difference, which is not. Now, if I look at a broad region from 32 to 42 eV, you see these asymmetries persist over the whole region. And now, if we integrate over all energies and fit to our analytic parameterization, that for linear polarization, in which you ionize the 1s electron in helium, you can parameterize it this way as intensity over some reference value to the 3/2 power. This is the carrier envelope phase, and k, the magnitude, and theta k, the phase, are a complex dynamical parameter that can be fit to the two-electron time-dependent Schrodinger equation results that we obtain. And you can see that the fit is perfect. This form, analytically predicted, fits the numerical results perfectly and determines the values of these two parameters. Also, the difference between projected on the uncorrelated and correlated persists. That there's a difference in the magnitudes. Correlation does have an effect. I could go on and show ionization with population of 2s, 2p, but in view of time, I will speed by this, covering it very quickly. This is the positive z-axis, this is the negative z-axis. This is the leaving helium ionized with the ion excited to 2s state or to 2p state. Along the pi direction, you have the opposite behavior. Along the negative z-axis, you're more likely to excite to the 2p state than the 1s state, whereas along the positive z-axis, you're more likely to excite the 2s electron than the 2p state. And of course, you see in this region all sorts of different even and odd parity, doubly excited states converging to n equals 3. And this shows the difference. You see almost mirror images of each other between 2s and 2p in the difference, and they flip sign. And this is the energy integrated results for producing 2s or 2p and fitting to our perturbation theory formula. You see the fit gives a perfect fit. And these energy integrated asymmetries for producing 2s state or producing 2p state are very different from one another. And if we show you the values of the parameters, you see that we extracted the intensity dependence. So using pulses of 1 petawatt and 2 petawatt produces almost no change. It should produce 0 change, but it produces almost no change in the magnitude of the 2s parameter, in the magnitude of the 2p parameter, in the phase of the 2s parameter, or the phase of the 2p parameter. So independent of the intensity, which is important because experimental pulses sometimes have varying intensities. They have an envelope. This parameterization is not sensitive to that. These dynamical parameters can be determined experimentally if one can get into this region. So to conclude these results, few cycle attosecond pulse asymmetries in ionization of helium can be amplified by orders of magnitude in the vicinity of 2 electron resonances or for exclusively 2 electron processes, that is excitation. These are the key references. And the collaborators on all these works are Jean-Marcel Mboko-Jokop, who is now a research assistant professor in Lincoln, my former postdoc, Su-Chin Hu, who is now in Rochester, my former postdoc, Misha Frolov, who's back in Russia. He's head of the department there, a long-term collaborator there, Nikolai Manikov, my former postdoc, Langyu Peng, who's now an associate professor at Peking University, and former postdoc, Evgeny Konin, and a student at Peng. And that's it, I think. Yeah. Thank you.
Questions?
Yes.
So I could choose my frequencies of 2 frequencies so that a 2 photon and a 1 photon process would interfere. Now I think you're doing it sort of the overlap region between 2
That's
broadband
exactly
buses.
right.
So I could make it much more efficient, I think, to make these currents and so on. So my question, so first I could do that, and I could probably do it technically much easier. Can I learn something important about 2 electron correlations from these kind of measurements?
Yes.
Yes.
I mean, by extracting the vectors and the carrier lobe phase dependence analytically, you can fit the dynamical parameters and then ask theorists to calculate those parameters, and that is a more efficient way of seeing how good the theoretical models are.
So how much could I lower the intensity? How close could I bring it to reality? If I chose my frequencies out of a harmonic train, out of the frequencies in harmonic train that were a factor of 2, one from the other.
We see these asymmetries beginning around 10 to the 14 mots per centimeter squared. So we chose 10 to the 15 because then they're dramatic, but we begin to see them, and certainly in these regions where you see these doubly excited states, these sharp resonances should be easily detectable, even for weak intensities.
I wonder if we couldn't bring the intensity down a lot. Maybe we'll pass it on to somebody else.
But 10 to the 14 is what Mark Vracking and Zhenggu Cheng are promising that they will achieve this year, well, they said it for last year, but now they're telling me this year, and these asymmetries should be observable with of the order of 10 to the 14 or higher.
When you look at the interference between a single photon and two photon
Yes.
absorption, is this not only valid in a perturbative definition of the sense?
Yes, yes.
Right? So if you have a strong field, then you can't distinguish.
I think we have a
between the
long
sense.
way to go, a long time to wait before you have strong field attosecond physics. I mean, attosecond pulses are very, very weak now, and perturbation theory will work up to 10 to the 16 watts per centimeter squared, I think.
But your formulation was true for all pulses, right? Not just very short
Well, but,
attosecond pulses.
you know, when the different orders of perturbation theory become equal to each other,
Right.
perturbation theory breaks
Right,
down.
right.
But I'm saying that won't occur until you get above 10 to the 16 watts per centimeter.
Any additional questions for Professor Starace? I have one more.
Yes?
What happened to the use of the board?
Well, nobody asked a question. I was going to use the board to answer questions. Yes?
On that.
Suppose you do, as you use strong field, you can no longer use perturbation theory. But do you expect the electron-electron correlation to be the same?
Do I expect
Electron-electron
the
correlation?
same when you have strong field?
Right, that should be the same, right? That should be independent of the field.
Yes.
So whatever you calculate, so if you can calculate the electron-electron correlation with the perturbation theory, you expect the same.
But
I know.
our numerical calculations treated correlation for helium exactly. I mean, we solved the two-electron tiny penetrator equation, and there were no perturbative approximations. What I'm saying is that the results of those fully ab initio numerical calculations could be analyzed using our perturbation formulas. Because, you know, when you do a numerical calculation, you get out a result and the students think they're done. But the real work is only beginning because you have to figure out what do my results mean. And being able in attosecond physics to have perturbation theory to help you analyze your results and also to predict new things you can do, that gives you a big advantage that doesn't exist in strong field physics where you can't, perturbation theory doesn't work.
The students are obliged to follow, so join me in thanking all of the lecturers this morning. That can be done over lunch. Of Ken and Paul and Tony. So thank you very much for all of you. Before I let you go, we'll come back here at 5:30 for the lecture by Lars Madsen, and before dinner, and then of course there's another one after that. This afternoon is a free time, okay? So try to enjoy it. Tomorrow there's going to be biosphere tour, and other days we'll have to sort of see according to the.
So this afternoon we do homework.
Huh?
This afternoon we do homework.
Yes. There are two homework problems.
So are you going to get slides for the morning?
Yes, I'm going to. Well, I mean, I cannot do it myself. I will have to ask them, right?
So if you got the homework, you just slide.
That's right. This will be very good if they will do it. I will individually approach them to email your slides to Maggie.
I
can do that, yes.
Email them.
I mean, the file is too big. You need a flash drive.
So then I will ask Naomi
Upload it to Dropbox.
open up a drive so you get something to drop it into.
Yeah.
But I don't know what the requirements are in your email.
No, this is for dropping, so she will send